Hi everybody and welcome to our latest video on the AQA GCSE paper 2, and today we're going to give you a bit of a walkthrough of the units in the paper and what to expect, as well as some key content, tips and strategies for you to be able to go in with confidence. So let's get started. So paper 2 is structured in the same way as paper 1. Triple students will be doing 1 hour and 45 minutes for 100 marks worth of questions, and for the combined students you'll be doing 1 hour 15 minutes worth 70 marks, and this makes up 16.7% or so of your combined science GCSE. And you'll also be expected to see a range of multiple choice, short answers, structured answers and open response as well. And just remember, this is the last chemistry paper, so keep the energy up and you'll be absolutely fine. So what topics are covered? As you'll know, that there are 5 topics that will be covered in the chemistry paper 2, so it's quite a lot of things to remember and go through. So we've got C6, which is the rate and extent of chemical change, C7, organic chemistry, C8, chemical analysis, C9, the composition of the atmosphere, and C10, using resources. And as always, the specification is what you should be using from the start of your final days of revision for this, just to make sure you're clear on what you need to be doing and what you're expected to answer. But that's something that we'll go through today, so that'll hopefully give you a good stepping stone to then complete your final stages of revision going forward. So for each paper, you've got to remember you've got your required practicals as well. And it's very easy to forget these, but they're equally as important as the unit content because these can make up whole questions just as easily. So for each practical, you need to make sure that you cover your hypotheses, the variables, equipment, method, data collection, data visualization, and some evaluative points as well. And I know I've gone through these in every video so far, but I just really want to emphasize how important they are. But here I just also want to go through what you might be expected to answer for each of the practicals in this paper. So if we start with rate of reactions, there is a triple and combined required practical. So you all have done this practical, and they could ask you to describe how to investigate the effect of concentration on the rate of reaction, which is linked to the subject content. They could also ask you to identify the variables and explain how you can use those to measure the rate. So you need to know maybe how a gas syringe would be used, and the relevance of the disappearing cross and timing that point when it disappears, and then also be able to explain your result using particle theory. So that's linking it to the subject content and showing that you can really apply your chemistry knowledge. And similarly for chromatography, it's a triple and combined required practical, and one of the main things they might expect you to do is calculate and potentially explain the RF values from a set of results that they give you in the question, but you also might just need to interpret a chromatogram as well. And finally, also you might be able to explain how to separate substances using chromatography. And I know that's a C1 topic, chromatography and separating mixtures, but because you've got the required practical here as well, you could easily get asked about that on this paper as well. And for water purification, which is from the final topic, one of the things you might need to do is describe a method to purify water. So relevance could be filtration and distillation. And then you also need to evaluate different methods of water purification. So you did a required practical in your class, but you also might be given a slightly different method for water purification, which might be done in a different place or for a different reason. And you need to be able to kind of talk about what the pros and cons of that might be, and identify risks and improvements to practicals as well. And I put that one there, but it could be relevant to all of the practicals that come up on this paper. And identifying ions, finally, is a triple science practical only. So for these ones, you would probably need to be able to describe the positive and negative ion tests. So that could be the flame test, the precipitate tests, or the carbonate test, for example, and interpret those results from potentially unknown samples. So your colour changes, which you've covered in the lessons, will be something that will be relevant to know in these kind of questions. And there are ways that, if you can memorise them, can be a good way of picking up some extra marks. And finally, if you're a higher tier student, you might need to write ionic equations as well. So those are the main things that we probably want to be focusing on as we go into the required practicals. They could ask you about something else, but those are the kind of the most common kind of things that they might ask for each question. So as well as making sure you're confident on the 7 points for each of these practicals, I would make sure you take some time to consider what you would say if you got asked a question like that with those specific command words. So the key ideas for chemistry paper 2 are quite similar to the ones in paper 1. So understanding that the shapes of molecules and the way giant structures are arranged is important to the way that they behave. And also there are barriers to reactions. So reactions occur at different rates. Obviously, that's very relevant to this paper. And that also chemical reactions occur through proton transfer, electron transfer, and electron sharing. And I know that a lot of these principles we learn in C1, and C2, but because chemistry is a really interwoven subject. Everything you kind of learn can be relevant to another unit. So you really want to make sure you don't kind of neglect making sure that you keep all of these key ideas in mind, because they could hold relevance to questions in paper 2 as well. And energy is conserved in chemical reactions, so it can neither be created nor destroyed. We've learned that in physics as well, and it's also relevant to chemistry, and always something that can come up in questions and you need to remember. And then you've also got all of your key ideas which are relevant across the whole sciences, and kind of think in a way that we can start thinking scientifically. So that's things such as using models and theories, the assumption that every effect has one or more cause, which is relevant to practicals and choosing your variables and controlling other variables as well. That change is driven by the differences between different objects. Many interactions can occur over distance without direct contact. That's particularly important to physics paper 2, which we'll go through in our next video. And that science progresses through a cycle of the hypotheses, experimentation and observations, theory development and review, and that quantitative analysis is a central element of theories and the methods that we've discussed. So really getting these kind of principles in mind can help you approach those required practical questions and just your chemistry paper in general. So as with paper 1, you're assessed through AO1, demonstrating your knowledge and understanding, AO2, applying that knowledge and understanding, and AO3, being able to analyse information and ideas to evaluate or make judgments or draw conclusions, and that could be involved in proving experimental procedures as well. And I think, as we've said, AO3 will make up about 17 to 23% of the marks, whereas AO2 will make up, and AO1 will make a much bigger proportion of your marks. But AO3 ones can be really, really beneficial for getting those extra marks, which could make the difference between getting a grade and not getting a grade. And with your command words, in a similar way to paper 1, you can kind of get an idea of the kind of question or the kind of skills that you need to be showing based on the command word. So AO1 is likely to be an identify, a give or a state, or just simply asking you for a specific answer. AO2 will be more about explaining, completing, calculating, comparing, and often giving you some contextual information for that as well. And then AO3 will be command words such as analyse, predict, justify, evaluate, suggest and plan as well. But I think, as we've said before, the AO1 and AO2 marks are relevant within AO3 questions as well. So particularly on big answers, you kind of need to be making sure you're considering, or it could be marked on all of these bits, so I can't just jump straight into my analyses. I might need to give some context from AO1 and AO2 first. It's always worth keeping these in mind. So we're going to go through each of the units in turn. We're going to go through the key concepts and then give you some practice questions to consider and then try as well. So if we start with the rate and extent of chemical change, the key concepts are the idea that the rate of reaction is the quantity of reactant used or the product formed divided by the time taken, and that the units of that will be grams per second, centimetres cubed per second, and if you're HT only, potentially using moles as well. You need to be able to interpret graphs of the rate of reaction, so that could be a reaction progress over time, so that could be a slope. If you're a higher tier student, you need to be able to use tangents on those graphs to then calculate the rate of reaction using our equation at the top from the information that you can obtain from the graph. You've got the required practical, as we've said, so how the concentration will affect the rate of reaction, which can be determined through either measuring the colour change or the change in gas volume. The factors affecting the rate of reaction, so you need to know how temperature, concentration, pressure, surface area and catalyst all affect the rate of reaction, and apply collision theory to this, so the idea that particles must collide with enough energy, known as the activation energy, in order for a reaction to occur, and that catalysts can speed up the rate of reaction by lowering that activation energy without being used up. You also need to be able to recognise, interpret reaction profiles, and you might need to compare with and without catalysts. And there's I think with a lot of these are very long units, so there's a lot of things you need to know, but you can see how this whole unit kind of interweaves into one cohesive bit of knowledge. You also need to understand reversible reactions, so the idea that products can react to reform the reactants that originally reacted together to form that product, and that energy in reversible reactions is important to be able to determine. So if it's a forward reaction, it's the exothermic, and if it's a reverse reaction, if it's endo, and vice versa. You need to be able to recognise which one's which. And you also need to appreciate the idea of the dynamic equilibrium, where the forward and reverse reactions are occurring at an equal rate in a closed system. And if you're higher tier, you also need to be able to apply the Chanteler's principle, which is the idea of the equilibrium shifting. So the equilibrium can shift to oppose changes in concentration, pressure, or temperature. And the effect of concentration in this is that it can change the product or reaction balance until the equilibrium is restored. So the idea that if there's a change, then something will change within that equilibrium to make sure that the equilibrium can be restored. And same, you need to be able to explain this in the context of temperature, so shifts in equilibrium towards the endothermic or exothermic side depending on how it is changed, and the effect of pressure as well for gases. So for gases, equilibrium shift from side to side with either fewer or more molecules depending on whether the change in this closed system was an increase in pressure or a decrease in pressure. So let's go through a few examples of questions that you might see, which should hopefully give you a good idea of what you kind of might be expected to do with this unit. So example 1 is to calculate the mean rate of reaction if 48 centimetre cubed of gas is produced in 16 seconds. So for this question, you need to use your formula of rate of reaction, so rate equals quantity over time, and substitute these values incorrectly to your equation to get the correct answer. So the rate equals 48 divided by 16 seconds, which gives us 3 centimetre cubed per second. And for this particular question, we didn't get given the unit, so you'd also get a mark for providing the correct unit. And for example question 2, explain using collision theory why increasing the temperature increases the rate of reaction. So for this question, you need to mention the more frequent collisions that have more particles having the activation energy. So the few things you need to talk about there, and also make sure you're using the correct terminology. So here's an example answer. At higher temperatures, particles move faster. That would be 1 mark, which this leads to more frequent collisions. Another mark. More particles have energy equal to or greater than the activation energy, 1 mark, and therefore more successful collisions occur in a given time, increasing the rate. So we're talking about what happens, particles move faster, what the consequences of this is, that's explaining, another mark there. And we're also then applying it to increasing the rate of reaction, so talking about the fact that there's more particles with the energy and more successful collisions occur in a given time, and we know that rate is related to both quantity and time. So we've put those together to give our explanation. So question 3, describe a method to investigate how changing the concentration affects the rate of a chemical reaction. So here, this is referring to the required practical that we've done. So we want to be referring to our variables, the measurements, and also how you'll keep it a fair test, because we're trying to give an overview of a method. So somebody reading it would be able to understand what the method entails. So for this answer, I would say something along the lines of use different concentrations of acid while keeping the other variables the same. So we're going to have concentration as our independent variable. Add acid to a measured amount and measure the volume of the gas produced. So that's talking about what we're doing to obtain a measurement. And then use a gas syringe, again referring to our equipment, or an inverted measuring cylinder to collect the gas, and repeat for each concentration and then compare the results. So there's many more things you could say in this answer to kind of describe a method, but because it's only 4 marks, we only need to be making 4 key points. So question 4, how can you calculate the rate of reaction at a specific point on a graph showing volume of gas over time? So for this question, we need to be understanding the use of tangents and gradients to find a result at a specific time. And I just want to give you an example here. So we're talking about using the gradient, so the change in y divided by the change in x, which is the equivalent to determining a rate between the volume produced in a given time. So let's say this could be an example answer for a higher tier paper. You might be asked to do this description, or you might literally just be given a graph and asked to determine the rate at a specific point in time, because as you can see, the rate has changed a lot, but we're thinking about how the rate has changed at this specific point, just in our example here. So first mark would be for drawing a tangent to the curve at a specific time point, which we've done there with our orange line, and then calculating the gradient of the tangent, which is, as we said, the change in y, so the change in the amount of product made divided by the change in x, the time gone. So if we go back to our original rate of reaction, quantity over time is the rate. So this is the exact same thing basically, and then make sure you give your answer to the correct units. Question 5, evaluate the advantages and disadvantages of using a higher concentration of acid in a reaction with magnesium. So this is kind of like leveling up a little bit from the question we had for question 3. We're going to be using a lot more AO3 skills and knowledge here to give both sides of the argument. So what happens to the rate of reaction at higher concentrations, and because we're trying to think about what a disadvantage could be with a method, we want to be thinking about safety and controlling the reaction. So this is really what the examiner here wants you to be thinking about. So the mark scheme is, as always, for a 6 marker quite vague, but for that level 3, that 5 to 6 marks, they're looking for a detailed evaluation of both the advantages and the disadvantages. When you look on examiner reports, often they will say in some questions like this that students were able to do one of them but they didn't do the other. And you also want to be given a clear and accurate use of the collision theory and the safety and industrial implications. So the collision theory is basically applying it to the scientific principle that you understand about how higher concentrations affect the rate of reaction, and then applying that to the real world context, which we've been given here. What could the impact of that be? And then for level 2, 3 to 4 marks, you're kind of doing a similar thing. You're given a clear explanation of at least one advantage and disadvantage, and making at least some reference to collision theory, but this won't be an incredibly well developed answer which would fit into this bracket. And then for level 1, you might be able to get 1 or 2 marks if you're only able to either give an advantage or a disadvantage, and you might not be referring to collision theory, and also there'll be limited use of those scientific terms that we've discussed at the higher levels. So this is an example of a 6-mark answer. So let's give this a read through and understand kind of how all of it's kind of relevant. So a higher concentration increases the rate of reaction, and this is because there are more acid particles in the same volume, which leads to more frequent successful collisions. So that's explaining collision theory. However, the reaction may become too fast and hard to control, so it may be too vigorous or unsafe, especially in a school lab where hydrogen could build up and be flammable. The production of gas, hydrogen gas, too quickly, which could be dangerous. So we've talked about it in a school setting, which is always useful to kind of think about because that's ultimately where you did your practicals, and you would have seen this reaction at some point with magnesium and hydrogen letting off a lot of gas. Usually in this kind of question, they would give you a clue for that as well in the context above. So you want to kind of be thinking, right, what would happen if this reaction was really, really, really quick? And that's kind of what they're getting at here. So let's go through the rest of the answer. So in industry, this could increase the risk of pressure buildup or cost due to safety controls, because it would require a lot of material in order to prevent the equipment from exploding, basically. So therefore, while increasing concentration improves the efficiency, so that's an advantage, safety precautions must be taken to prevent uncontrolled reactions. So we've kind of gone through using collision theory to talk about how it could be an advantage, but then also talked about our safety concerns as our disadvantages to get to a balanced, well-meaning conclusion. So now it's your turn to do some questions on C6. So you can either have a go at our range of C6 questions below this video on Revision Hub, or you can use the link to head over to our revision clocks for C6. And then once you've done those, you can come back to this video and we're going to go through C7. So welcome back. I hope you enjoyed your C6 questions and revision clocks. So we're going to go through C7 now, which is organic chemistry. So the key concepts for organic chemistry, we're going to start with crude oil. So the idea that crude oil is a finite resource and formed from ancient biomass. Hydrocarbons, so the idea of hydrocarbons, that they are made up of molecules of hydrogen and carbon only. And that alkenes are saturated hydrocarbons with a general formula of CnH2n+2. That fractional distillation separates crude oil into fractions by boiling points, and that petrochemicals, which are fuels such as petrol and diesel, and feedstock for making polymers, detergents, etc., are all things which can be made from fractional distillation. So these are our kind of key concepts for organic chemistry. So the idea of crude oil, which is where hydrocarbons come from, and then a basic outline of why they are relevant in our society today. And hydrocarbon properties will change with longer chains. So longer chains have a higher boiling point and viscosity and a lower flammability. So you need to kind of be able to describe how the properties change depending on the size of a hydrocarbon molecule. And also understand that combustion, which is one of the main reactions we see in industry with hydrocarbons. You've got the complete combustion, which produces carbon dioxide and water from hydrocarbons. And also cracking is another reaction we need to be able to know about, which is the breaking of longer hydrocarbon chains into smaller alkenes and alkanes, which are potentially more useful products. And those alkenes are unsaturated hydrocarbons, so they have that CC double bond, and they're more reactive than alkenes because essentially the double bond gives an opportunity for a reaction to happen. And in order to test for alkenes, we use that bromine test, which you hopefully remember, where the bromine water will turn colourless. You also, for chemistry students, so that all of that was relevant to everybody. I think from now on, it's all chemistry or higher tier only. So for combined students, don't worry, we're going to go through some questions, so you can either skip to that point now or just stick around to listen to the other key concepts, completely up to you. But for chemistry students, we need to know that alcohols have a functional group of an OH, so that's how you recognise an alcohol, and you need to be able to recognise and appreciate the reactions with sodium, air, water, and oxidizing agents. And fermentation is one of the most common reactions that alcohol is produced from, so You might see that in yeast, for example, where sugar with yeast make ethanol in their respiration, in their anaerobic respiration, and for that you need the conditions of about 37 degrees and no air because it's an anaerobic reaction. You also need to know about carboxylic acids, so you need to be able to recognise them, and for that the functional group will be a COOH molecule attached to one of the hydrocarbons, and these are weak acids which have reactions with carbonates, waters and alcohols, which you need to be able to recognise. We also have the reactions of addition polymers, which are made of alkenes, and they don't have a byproduct, and they essentially have those repeat units of called monomers, and this makes them incredibly useful materials. You also need to know about condensation polymers as well if you're higher tier only, and those are monomers with two functional groups which produce polymers and a small molecule which is typically water, but both of these reactions can be used to form incredibly useful products. And then you also, if you're a higher tier student, need to be able to recognise amino acids. So those are in our bodies and in proteins, and they contain an NH2 molecule and a COOH group on some point on their molecule, and those form proteins via those condensation polymerization reactions that we talked about. So you need to be able to appreciate that and recognise that those are produced, and then there's just a release of a small molecule at the end of it as well. And then finally, you also need to be able to apply these principles to DNA. So you know that from biology that a DNA is a double helix polymer, and you also need to know that these are made from nucleotide monomers, and there are also other naturally recurring polymers as well, which are similar to DNA, such as start cellulose and those proteins we just talked about as well. So that's kind of applying that organic chemistry to biology as well. So let's go through some example questions. So question 1 is a fairly simple question. So it's give the general formula for alkanes and name 2 examples. So I've given you a range of different alkanes there. So here we just, as it says on the tin, you need to recall and write that general formula for alkanes and name 2 specific examples. So as we just went through, the general formula is CnH2n plus 2. So for every 1 carbon atom, you would have 4 hydrogen because you've got 2 of n, so n is 1. So 2 of that is 2 plus 2 equals 4. So that's the general formula. And then 2 examples that you could give are methane and ethane. Those are the 2 smallest ones and typically just the easiest ones to recall. So I wouldn't overcomplicate that kind of question, just go for the basic knowledge. So example question 2 is describe how fractional distillation separates crude oil into fractions. So this is a 4-mark question, so we don't need to overcomplicate it, but we do need to mention all of the key steps. So we want to be describing the heating, which is what causes the reaction to take place in the first place, the relevance of boiling points and condensation to this particular method, and then link it to molecular size as well, because all of those points are crucial in order to explain, or describe rather, how fractional distillation works. So here's an example answer. Crude oil is heated until it evaporates. The vapour rises up in the column, which is cooler at the top. Different hydrocarbons condense at different heights, depending on their boiling points, and larger molecules condense lower down because they have a higher boiling point, and smaller ones condense higher up. So question 3, describe the test for an alkene and explain what happens. So we've already kind of briefly discussed this as we went through the specification, but what you need to do is state that test and the expected colour change, so the expected result, and to explain why that happens, link it to that presence of that double carbon bond. So our answer could be add bromine water to the substance. If it's an alkene, the bromine water will turn from orange to colourless, and this is because alkenes react with bromine due to the carbon-carbon double bond, and that would be 3 marks worth. And question 4, explain why cracking is important and what it produces. So here we are explaining the need for cracking, the process involved and its products in order to cover all of those 4 marks. So one of our answers could be there is a high demand for small hydrocarbons for fuel. So that's explaining the importance. Cracking breaks down long chain alkenes into shorter alkanes and alkenes. So that's explaining what it produces. It uses heat and a catalyst or steam. And alkenes are useful for making polymers and chemicals. So we're talking about what it produces, what it is and why it's important, how it produces us what we need it to. So now it's your turn to have a go at some organic chemistry questions. So you can either complete those questions, or if you don't feel quite ready yet, have a go at the revision clocks and then go back to the questions. And then once you're ready, we'll move on to C8. So now it's time to move on to C8. So the key concepts of C8 is firstly the idea of a pure substance. So you need to know that a pure substance is either a single element or compound, and that melting or boiling point of that element or compound is at a fixed temperature. And formulations are carefully designed mixtures. So that could be medicines, paints or fuels. So you need to know the examples of formulations. Chromatography, as we've already said, separates mixtures into its constituent parts using stationary and mobile phases, or the principles of those. And an RF value, which you obtain from a chromatography procedure, is the distance moved by a substance divided by the distance moved by the solvent. And paper chromatography, in the results, if the substance is pure, you'll get one spot, and if it's impure, you'll get multiple spots. So that required practical of using paper chromatography to identify and compare substances could hold a lot of relevance to questions in this unit. So you need to make sure you really know that required practical well and be confident to calculate RF values and explain whether you can determine if a substance is pure or impure. You also all need to be able to recognise the gas tests and explain or describe the test and what the result would be, or vice versa. You get the result, you need to be able to identify what gas has caused that to happen. So being able to identify those gases. So if it's hydrogen, you do the lint splint test and you'll get that squeaky pop. If it's oxygen, a glowing splint will relight, and carbon dioxide will turn lime water milky, and then finally chlorine will bleach damp litmus paper. So if you see any of those procedures in a question, you know immediately it's referring to that gas. So for chemistry only students, you also need to be able to recognise the ions from flame tests. So what colour each of these metal ions produces. So lithium produces a crimson flame, sodium a yellow, potassium lilac, calcium an orange red, and copper a green. And you also need to be able to remember and recall the results from metal hydroxides having sodium hydroxide added to them. So aluminium, calcium and magnesium will all produce a white precipitate, and only aluminium out of those will dissolve in excess sodium hydroxide. If it's copper, it will produce a blue precipitate. Iron 2+ will be a green, and iron 3+ will be a brown. With all of those, I found it really useful to produce a table of those and just have a look at that just every day close to the exam, and really just try and get those in your mind, because they're not easy ones to remember. There's no logic to it particularly, so it's just one of those you really just need to remember. But if you can, it's a really easy way to pick up some extra marks. So you also need to be able to know the test for carbonates. So they react with acid to produce carbon dioxide, and as we've seen with the gas test, that will turn lime water milky. You also need to know the test for halides, so that is adding silver nitrate to nitric acid, and if it's chlorine, it will produce a white precipitate. Bromide, it will produce a cream precipitate, and iodide a yellow precipitate. You also need to know the test for sulfates, so that's barium chloride plus hydrochloric acid, and if it's a sulfate, a white precipitate will be produced, and that's also a very important one to remember. And then overall, it's just being able to apply those to your required practical situations. So the test for unknown ions using either the flame test, precipitate, or gas test. So often these will kind of all be used in turn, and then you'll have a collection of unknown ions, and then you need to do each of these tests on each of them in order to kind of deduce which one's which. You also need to know about some instrumental methods which can be faster, more accurate and sensitive than the tests that we've kind of gone through today. So an example of that is flame emission spectroscopy, and that is where metal ions emit light, and then you use the line spectra to identify the metal and even the concentration. So that's the big benefit of using that one. It's also a more quantitative procedure than any of our qualitative ones here. So going back to our scientific principles, that's where you could be asked about explaining why the flame emission spectroscopy is more reliable, and also other benefits to it as well. But obviously it's much more expensive than our qualitative ones we've done in class, so everything comes with its advantages and disadvantages. So let's go through some example questions. So example 1 is define a pure substance in chemistry and explain how you could test if a substance is pure. So for this one, you need to recall that chemistry definition of purity and describe a valid test, which involves the melting and boiling point, because we know that's why having a pure substance is really important and relevant. So an answer could be that a pure substance contains only one element or compound, as we've said in our content section, and you can measure its melting or boiling point, and a pure substance melts or boils at a specific fixed temperature. In this answer, you could have also said you can refer to a reference melting or boiling point, which is internationally agreed, in order to see whether it matches it, basically. So question 2 is describe how paper chromatography separates substances, and in your answer include how you can use it to identify if a substance is pure. So we've already gone through this quite a bit already, but for this question you need to explain that process of chromatography, the use of solvents, and identification using spots. So I've given a little diagram there. An example answer for this could be that substances in a mixture move at different speeds in the solvent. They separate based on how strongly they interact with the stationary phase. A pure substance will produce one spot, a mixture will produce more than one spot. So in our example here, this is definitely a mixture or an impure substance, because we've got lots of different solvent fronts here. So question 3 is give the results of the flame test for lithium, sodium and potassium ions. So this is 3 marks because you need to give the results for 3 different flame tests. So simply state the correct flame colour for each metal ion. So this is just something you need to try and remember. So lithium gives a crimson flame, sodium gives a yellow flame, potassium gives a lilac flame. That's just an example of what you might be wanting to say here. And you can't see this all right here, but this is the example of the kind of table that you want to be making. So you can either take a screenshot of this now or you can make your own. And question 4 is describe a chemical test for sulfate ions and state the result if they are present. So this is similar in that you just need to recall those reagents and the expected positive test result. So add barium chloride solution in the presence of dilute hydrochloric acid, a white precipitate forms, which indicates that sulfate ions are present. So that's just what we've gone through with the content there, and it's just basically relaying that information. And question 5 is describe how to carry out flame tests to identify metal ions. So outline those steps clearly in order and show that you really understand the importance of different parts of the method. So that could be the importance of using a clean loop and in order to produce an accurate flame colour. So use a clean wire loop to avoid contamination. Dip the loop into the metal ion solution. Place the loop in the blue Bunsen burner flame. It's really important to state that as well, and observe and identify that flame colour change. So for example, lithium could be crimson, but they haven't asked you to give an example here. I've just put that in as a bit of extra. But on this kind of question, it could be easy to forget to talk about using the clean wire loop. But it's one of those which is, we don't have to be mentioning every single control variable. But in this case, if you don't clean the loop, then you just won't be producing an accurate result at all, because then you'll be mixing metals and you won't be able to get any reliable results. So that is one of the fundamental steps in this method in order to produce a result in the first place. So hence why it's really important to talk about it in this kind of 4-mark answer where you're describing the test. So now it's your turn again to have a go at either the revision clocks for C8, or if you feel confident and ready to have a go at some C8 questions, you can find them below this video, and then we'll move on to our final 2 topics of the atmosphere and then using materials as well. Okay, so now we're going to move on to our penultimate unit, which is the composition of the atmosphere. So the modern atmosphere is made of about 80% nitrogen, about 80% oxygen, and then small amounts of carbon dioxide, water, vapour, and the noble gases as well. But the early atmosphere was slightly different, and due to volcanic activity that led to that increase in carbon dioxide and hydrogen vapour, nitrogen, traces of methane and ammonia as well. And then the oxygen increased over time from that early atmosphere to our modern atmosphere due to algae and plants photosynthesizing, which released oxygen. And carbon dioxide decreased because carbon dioxide gradually dissolved in oceans. It was also locked in sedimentary rocks and stored in fossil fuels as well, so quite commonly plankton. But that's basically explaining how the atmosphere came to how it is now. And also, we also need to appreciate the importance of greenhouse gases in the atmosphere. So those are things such as carbon dioxide, methane and water. They basically trap that infrared radiation, which maintains the Earth's temperature. And obviously, we always talk about greenhouse gases in a negative way, but because there are too many of them. But having the quantity that we've had over the development of the composition of the atmosphere over the course of millions of years has actually maintained the Earth's temperature to how it is today. Otherwise, it would be substantially colder and life wouldn't probably, as we know it anyway, be able to exist. So that's the importance of greenhouse gases. But as we know that human activities have increased carbon dioxide and methane levels to levels which are detrimental to the Earth and our way of life. So carbon dioxide has come from through burning those fossil fuels and deforestation as well. So carbon dioxide has been released, and there is also less carbon dioxide being taken in by forests and trees. And the increase in methane has come from cattle farming and landfill as well. So we also need to be talking about global climate change, as we've kind of just briefly mentioned there with greenhouse gases. So we need to think about the effects of climate change, which can be rising sea levels, extreme weather, habitat loss and food insecurity are the main ones. And we also need to understand and appreciate the concept of the carbon footprint, which is the total greenhouse emissions over a product's life cycle, and how we could reduce those footprints, which could involve the use of renewables, be more energy efficient, and also in having some carbon capture, either directly or indirectly. But as we kind of see as we go through this, that cost and lifestyle changes are barriers to people being able to reduce those footprints. We also need to know about some combustion pollutants. So carbon monoxide, which comes from incomplete combustion, is toxic and is colourless, which makes it very dangerous. You also have sulfur oxide and nitrogen oxides, which can contribute to acid rain and respiratory problems, and then also particulates as well, which cause health issues and global dimming. So you also need to be able to recognise those molecules and the effects of those on either the Earth or humans. You also need to be able to recognise some pollution sources, so that includes fossil fuel combustion, that incomplete combustion we just mentioned, and high temperature engines as well are the main ones. So let's go through some examples of some C9 questions. So question 1 is state the 2 main gases in the Earth's atmosphere and their approximate percentages. So that's again back to our first few points of C9. So recalling the names of the 2 main gases and their rough proportions as stated in the specification. So nitrogen, approximately 80%, oxygen, approximately 20%. So it's a nice simple 2-mark answer there. Question 2 is explain how the amount of oxygen in the Earth's atmosphere increased over time. So this is going back to our talking about how the composition of the Earth came to how it is. So we want to be mentioning photosynthesis and when it began, and include the organisms involved and that chemical process, which leads to the oxygen being released into the atmosphere. So algae began photosynthesizing about 2.7 billion years ago. Photosynthesis produced oxygen as a byproduct, and over time, more plants and potentially algae evolved and the oxygen level increased. So that's explaining those 3 points there, which kind of led to the oxygen increase in the atmosphere. So question 3 is moving on to our global climate change part of the topic. So describe 2 human activities that increase the amount of greenhouse gases. So for this question, I would probably stick to giving one source of each carbon dioxide and methane just to help me separate my answer a bit, and describe how each activity contributes to emissions. So I would say something along the lines of deforestation reduces the number of trees that absorb carbon dioxide, and methane is also released from landfill as waste decays. So we've identified the greenhouse gases and described how a way that they are released. So question 4 is describe what is meant by the term carbon footprint and give one reason why it can be difficult to reduce. So here we just describing, defining that term, and then giving a clear and realistic barrier to the reduction. So an example answer could be that carbon footprint is the total amount of greenhouse gases released over the full life cycle of a product or activity. And these include carbon dioxide and methane. It just gives a bit more of an extra point to really explain what carbon footprint is. It can be difficult to reduce due to the high costs, which could be a mark. And I've also said here, all changes needed in public behaviour. So what I've done there is given 2 reasons. You only need to give one, but potentially if you're not very confident on one of your answers, it could be worth putting another one just in case you feel like you're semi-confident on both of them and you just want to put both there to increase your potential of getting the mark. If you have time to do that, that can be worth doing. So question 5 is our final question for C9, and it's a lovely 6-marker. So discuss the reliability of evidence for climate change and suggest why some people disagree with it. So we're talking about why people disagree with it. So it does refer back to our scientific principles. So we want to be talking about peer-reviewed science, difficulties in modelling, and potential reasons for people disagreeing with climate change, which I think, as we've seen in our lives, can be a result of media or public scepticism. So let's quickly go through the mark scheme first. So if we want to be getting a level 2 answer, so that's 3 to 4 marks, we want to be given a clear mention of the evidence and at least one reason for the disagreement, and at least partly starting to explain that uncertainty or media bias. Whereas if you're doing level 1, you might give a basic statement about climate change and the disagreement at hand, but it's not really explaining that or giving any scientific backing for your answer. But really what we should all aim for is that level 3, so that 5 to 6 marks, where it's a well-developed discussion with references to peer-reviewed evidence, the complexity of modelling, and how media or opinions influence perception. So that's what I need to do. If you get all of those, you should be in that level 5 to 6, that level 5 to 6 marks, that level 3 sort of answer. So here's an example that most scientists agree climate change is caused by increased greenhouse gases from human activity. Their evidence is based on peer-reviewed data and climate models. So we're talking about our peer-reviewed science there, and peer-reviewed science shows links between rising carbon dioxide levels and global temperature increases. And that shows links is really important because, as we'll go on to say, modelling the Earth's atmosphere is complex and involves many variables. So modelling includes some uncertainty, which makes it easier for non-scientific sources to present misleading or biased views because there are different ways of interpreting evidence, which may reduce that public trust. Some media reports focused on short-term weather changes or questioned the data, further leading to public doubt about climate change. And despite this, and it's important to say at the end, that scientific consensus is strong and evidence does support human-caused climate change. So that's going back to our original point about discussing that reliability of the evidence and how essentially we as scientists tend to come to that conclusion that the evidence is strong for climate change. But then we've also throughout our question discussed why the reliability is perceived by some to be lower than it should be, potentially for other things, and also discussed why people would disagree with it, linking it to both peer reviews, modelling, and the media and public perception of the scientific evidence. So now it's your turn to have a go at some C9 questions or the revision clocks. Have a go at those, and once you're ready, we'll come back for C10 and go through the final unit. Welcome back, and this is our final unit for paper 2 of chemistry, and that is using materials. So the Earth's resources are used for warmth, shelter, food and transport, and that's our main concept behind using materials. You have finite and renewable materials. So finite examples are coal, oil and metal ores, and renewable examples are more like woods and crops. Sustainable development is the idea that we are using materials to meet the needs of our current needs without harming future generations. And one of the other key concepts in using materials is the use of water. So potable water is water that is safe to drink, so it's low in salts or microbes, and it's not chemically pure. And we can make potable water using filters, sterilising it, using chlorine, UV light or ozone, and also we could also be desalinating salty water in order to make potable water in different regions of the world. And this links to our required practical, which is the analysis and purification of water samples, which uses different pHs, dissolved substances, and the use of distillation in order to purify water samples. We also need to know about wastewater treatment, so that process of screening, removing sedimentation, the anaerobic sludge digestion, and finally aerobic treatment as well. And you need to kind of cover all of those points in order to understand that wastewater treatment. And then moving on to a higher tier topic about alternative metal extraction to the kind of ones that we've learned in earlier topics in chemistry. So that includes phytomining, which is where plants absorb metal compounds, and bioleaching, which is where bacteria make leachate with metal ions. And those are kind of considered to be slightly more environmentally friendly and sustainable methods of extracting metals than the ones that we've kind of discussed through metal ores and earlier topics. So some more key concepts that everybody needs to know about are those principles of life cycle assessments, or LCAs, which is where we understand the life cycle of material from the extraction or the obtaining of raw materials through its manufacture and use all the way to it being disposed of. So we need to know how a life cycle assessment works and also the limitations of them, which includes not being fully objective and containing some bias or potentially being manipulated. We also need to all be able to recognise how we can reduce resource use, so that is through reducing, reusing and recycling, and also the benefits of it, so saving resources, reducing the use of raw material and cutting pollution as well. So the rest of our topics for C10 are going to be chemistry only, so if you're combined students you can move straight onto the questions or continue watching if you so please. So chemistry only topics, we start with recycling metals and gas, so how we can do that. So we can melt and reform metals and glass, or some might need separation before it, but there are ways in which we can do that, such as getting scrap steel into a blast furnace, and that's ways that we can recycle those materials. You also need to know about corrosion, so the idea that rusting needs air and water, which can be prevented with paint, oil and galvanization, which is and also sacrificial protection as well. So you need to understand the concept of corrosion and how it can be prevented. You also need to be able to appreciate the use of alloys, so those are mixtures of metals such as bronze, brass, steel and gold alloys, so you need to be able to understand what those are and what their uses can be. And the same thing with polymers, so you've got low density and high density polyethylene, which are made by putting organic molecules into different pressures and temperatures, and then also the principle of thermosoftening as well, which is where they're melted on heating, and thermosetting, which is where they're made more rigid and won't melt. So this is ways that we can treat polymers differently in order to produce very different materials. You also need to know about composites, which is where you have two materials, a reinforcement and a matrix, which produces a material with some properties that you really needed to have, which are unique and not typically found in nature. So that includes fiberglass and carbon fiber. You also need to be able to compare different materials such as ceramics, composites, polymers and metals, and match each of those to their uses. So these are all in the specification quite clearly outlined, and so you need to make sure that you go through each of those one by one and be confident answering a question on each of them. Some more concepts in chemistry only is the Haber process, which is producing ammonia from nitrogen and hydrogen gases. And you need to know where you get each of those raw materials from. So nitrogen from the air and hydrogen typically is natural gas, and also the conditions needed to make ammonia. So that's 450 degrees Celsius at 200 atmospheres in the presence of an iron catalyst. If you're a high tier student, you also need to talk about Haber process and the concept of it being an equilibrium, and that there's a compromise between the yield and rate of the reaction. You also need to be able to discuss the use of NPK fertilizers, which provide nitrogen, phosphorus and potassium to soils typically. So firstly, we need to know where they come from. So ammonium nitrate can come from the reaction between ammonia and nitric acid. Phosphate rock and acids produce fertilizer salts, and there's a few other examples that you need to know as well, which are in the specification. You also need to be able to compare the lab versus use in industry, so comparing the methods used to produce these fertilizers, the scale at which they're produced, their purity, and the risks and safety concerns which come through those as well. So let's go through some example questions from C10. So question 1 is describe how potable water is produced from fresh water in the UK. So this is an example that you would have learned in class. So we just want to be outlining those 3 key stages and link each of them to their purpose in order to really get each of those marks. So an example answer could be that fresh water is passed through filter beds to remove solids. Then it is sterilised using chlorine, ozone or UV light to kill microbes. The water source must first be suitable and low in salt. So we've described 3 key stages that must be taken into account in order to produce potable water, and described what type of water is appropriate for it and how we process the fresh water, and then finally how we sterilise it as well. Question 2 is a higher tier only question, but I put this in here for everyone to go through to kind of see another explanation question. So explain why the Haber process uses temperatures of 450 degrees Celsius and a pressure of 200 atmospheres. So here we're explaining that compromise we mentioned between the rate and yield. So we want to be using our ideas about equilibrium and costs as well. So an example answer here is that a higher temperature gives a faster rate of reaction but favours the reverse reaction. 450 degrees is a compromise, so it's fast enough rate but produces an acceptable yield of the product that we want, which is ammonia. Then we move on to pressure. Higher pressure increases the yield of ammonia as fewer molecules on the product side. 200 atmospheres is chosen because it makes it effective, but it's not too expensive. Any high pressure would be very expensive to create and could potentially be dangerous as well. So basically we've described there how the temperature and atmospheres are both used to give an effective reaction rate, but to minimise the negative consequences that could come from pushing any of them higher or lower. So question 3 is compare the life cycle assessment or LCAs of plastics and paper bags. So this is an AO2 type question. So we're comparing those main stages and the environmental impact of both of those materials. So plastic bags are made from crude oil, paper bags from trees. That's described in our raw materials. Plastic bags require less energy to produce but last longer. That's another mark there for a direct comparison. Paper is biodegradable, plastic is not. Again, another comparison there. And finally, plastic bags can be reused more times before break-in than paper bags. We probably should have mentioned then paper bags at the end. But that's given 4 comparisons of different stages of that life cycle assessment for 4 marks. Question 4, describe 2 methods used to prevent iron from rusting. So name 2 methods and briefly explain them. Paint or grease creates a barrier that stops air and water reaching the iron. So that's one method there. Galvanization uses a more reactive metal, which corrodes instead, which is that sacrificial protection we mentioned as well. So that's 2 methods and given a description of each of them for 2 marks. And finally, question 5 is suggest and explain 2 reasons why recycling metals is better for the environment than extracting them from ores. So suggest those 2 clear benefits and give a clear explanation for each of them relevant to the environment, because we just want to be talking about the environment here. So recycling uses less energy than extracting metals from ores. That's 1 mark, as we referred to energy. Because metal extraction often involves heating ores in furnaces, which uses fossil fuels. That's linking it to that first point about the use of energy, and we obtain that through fossil fuels. Recycling also reduces the amount of waste rock and land damage caused by mining. Again, that's specifically about an environmental consequence of mining for metals, which preserves habitats and reduces pollution. So we expanded on that third point there about why it's beneficial for the environment. So now it's your turn to have a go at either completing the revision clocks for C10 or having a go at those range of questions, or potentially both. And that's everything I've got for you today, and I'm going to leave you to it to either continue your chemistry revision or potentially move on to another subject now. All the best with your exam, and thank you so much for watching. Bye.